accelerating faster than a bullet, it releases a force that vaporizes water, leaving scientists questioning the limits of biology. What you're seeing is not a bullet impact, but the biological weapon of a creature, no larger than your hand. Meet the peacock mantis shrimp. Beneath its colorful tropical exterior lies the most advanced spring-loaded strike in the animal kingdom. Equipped with trinocular vision, in 12 color channels, it scans the seabed, targeting prey with military precision, leaving its burrow. The mantis shrimp patrols its territory. It is a highly active predator, looking for shelled victims. A rock crab enters the zone, unaware its calcified armor, which shields it from most reef predators, is about to be tested. These are the dactyl clubs. To understand how they shatter shells, we must look at the biological engineering of the joint. Antennae will pick up chemical signatures. The target's distance and shell thickness are calculated in milliseconds. The stalk begins. The mantis shrimp slides forward, minimizing water disturbance to avoid alerting the crab. The outer impact surface of the club is made of crystalline hydroxyapatite. It is harder than engineered ceramics. Beneath the hard crust lies a shock-absorbing layer of chitin. These fibers are arranged in a helicoidal, staircase-like structure. This helicoid design prevents cracks from propagating. When the club hits, the energy is dispersed, protecting the limb from self-destruction. The spring is held in place by a biological latch mechanism. Muscles contract slowly, storing energy without moving the limb. To store energy, the mantis shrimp uses a saddle-shaped spring. As muscles contract, this structure bends, acting like a compound bow. As the distance closes, the lateral extensor muscles contract. The system is fully charged, holding potential energy. Muscles generate power that no animal muscle could deliver directly. The latch is about to trigger. Release. The latch slips and the club accelerates forward at 23 meters per second. This acceleration is equal to 10,400 grams. That is equivalent to a bullet leaving a gun barrel. The acceleration is so extreme that the animal's body experiences massive recoil, anchored only by its specialized legs. Upon impact, the club delivers up to 1515 newtons of force to the target. This force is enough to crack the crab's armor instantly. But the physics of this strike do not end here. The entire strike takes less than 3 milliseconds, faster than the blink of a human eye. Because the club moves so quickly, it displaces water faster than it can flow back, creating a localized vacuum. The pressure drops below the vapor pressure of water, initiating a phenomenon known as cavitation. Localized vacuum created. Vapor bubbles expand instantly. These bubbles are filled with low-pressure water vapor, not air. As the club decelerates upon hitting the target, the surrounding water pressure collapses the bubble. The collapse is violent. The surrounding water rushes inward to fill the void, generating a massive shockwave. This shockwave acts as a secondary strike. It hits the target less than a millisecond after the physical impact.
The temperatures
inside the collapsing bubble reach several thousand Kelvin, generating a brief flash of light. This phenomenon, known as sun luminescence, proves the extreme energy concentrated in a tiny space. The combination of the physical club and the cavitation shockwave creates a double strike effect, destroying the shell's structural integrity. Even if the first physical strike misses the cavitation, shockwave alone can stun or kill the prey. The energy released is so intense It causes dissolved gases in the water to come out of solution. In the wild, speed is survival. The mantis shrimp must feed quickly before the scent of prey attracts competitors. The crab is incapacitated. The defense system of the shell has been completely bypassed. Despite hitting targets with bullet-like force, the club's specialized minerals prevent it from breaking. A second strike. The club hits the exact same spot on the carapace, sealing the crab's fate. The shell splits open, the prey is exposed, and the mantis shrimp can now access the nutrient-rich mussels. Using its maxillipeds, the shrimp feeds. This protein-rich diet is essential for maintaining its high-energy lifestyle. The mantis shrimp's hunting method is highly efficient, reducing the time spent exposed to larger predators on the open reef. Once fed, the predator meticulously cleans its sensory organs. Its eyes must remain clear for the next hunt. In captivity, this biology poses a unique challenge. Mantis shrimp are known to shatter aquarium glass. Seeing its reflection, the territorial shrimp perceives a rival, striking the glass with full force. The localized pressure exceeds the structural limits of tempered glass. A fracture network spreads. For this reason, professional aquariumists must house these animals in thick acrylic tanks, which absorb the impact. Acrylic does not crack under the shockwave, keeping both the animal and its keepers safe from biological bullets. The peacock mantis shrimp is a marvel of evolutionary engineering. Its strike combines material science and fluid dynamics. Researchers are now copying this helicoidal chiting structure to design next-generation body armor and aerospace materials. In the quiet depths of the tropical reefs, this tiny creature continues to wield one of the most powerful weapons on Earth. If human could accelerate at 10,000 grams, what would happen to our bones? Share your scientific theories in the comments. Subscribe to WITA for more deep dives into the biomechanics of the wild. See you in the next investigation.